Hi everyone. We are Team 12. I'm Kriti Shankarao and my teammate here is Swati Shri Chavli. And our project is about QLoRA, parameter efficient fine-tuning of quantized LLMs. So we'll talk about enhancing large language models using QLoRA, which is a parameter efficient approach to model fine-tuning. So in this project, we'll delve deeper into the applications of QLoRA, which is a quantized version of low-rank adaptation, which is LoRA. This enhances the performance of large language models. And here also we can see from the diagram so that it maintains the original computational efficiency by reducing the memory usage by efficient computation and also cost-effective scaling. So first of all, let's look at why we need to fine-tune large language models. Large language models are revolutionizing the way machines understand and interact with human language. However, out of the box these models are, they're all generalists. Fine-tuning will allow us to mold these general capabilities into specialized tools tailored for specific tasks such as summarization, sentiment analysis, or even answering medical questions and for specific data sets. This process is not only an effective way to enhance performance, but also crucial for adapting models to domain-specific requirements, thereby increasing their practical utility and efficiency in real-world applications. Fine-tuning is beneficial in a number of ways, and some of them are for the adaptation to specific tasks, improving performance on domain-specific data, and also for transfer learning efficiency. So what is QLoRA? QLoRA stands out in fine-tuning because it introduces quantization into the adaptation process. And it transforms the weight matrices of the low-rank adaptation or LoRa from high-precision formats to low precision. This innovation drastically reduces memory requirements and computational tasks without sacrificing the model's effectiveness. In a sense, QLoRA ensures that our fine-tuned models are not only accurate, but also incredibly efficient, making them suitable for deployment in environments where resources are limited. So here is the diagrammatic representation of what a fine-tuned model does. We can see how the memory is drastically reduced. So let's talk more detail about our project. Here we'll be looking at setting up an installation. Setting up the right environment is pivotal for the success of AI/ML projects. And for our project, we leveraged several key libraries. We used transformers for loading and operating pre-trained models, PEFT for applying the QLoRA adaptations, Accelerate to optimize the training process across available hardware, and datasets from Hugging Face for efficient data handling. Each of these libraries have played a critical role in ensuring that our model training and evaluation process run smoothly and efficiently. So here we can see one such pip command for the installation of the libraries required. So now we'll look at the dataset which we used, why we made that choice and what it looks like. Our choice of dataset was the dialog sum dataset, which is accessible through Hugging Face dataset library. It consists of about 13,460 dialogues, each paired with professionally written summaries. This dataset is particularly challenging and relevant as it encompasses a wide variety of everyday scenarios, making it ideal for training our model and to handle various conversational contexts. An example from the dataset involves here a customer's service interaction. So the dialogue here we can see is the person one asking, "Hi, I was wondering if you could help me with my order." and person 2 saying, of course, what seems to be the issue. So the summary of this would be that a customer seeks help with an order and the service representative responds positively. So here we look at the model configuration with QLoRA. So configuring the V2 model involved setting up QLoRA adaptations specifically tailored for the task of summarization. So we used 4-bit quantization to reduce the model's memory footprint. And the adaptation parameters were also carefully selected. A rank of 32 and LoRa alpha also set to 32. Targeting key transformer modules such as we can see it was Q, Prog, K, PROG, V, PROG, and dense as well. So these settings were crucial for achieving the desired balance between the efficiency and the performance during fine tuning. So now let's talk about how we prepared the model for the training, and Swati will continue further.
Yeah, so today I'm gonna talk about the training preparation that was done for the model. So training preparation involved several critical steps. We started by employing the auto tokenizer from Hugging Face to ensure that the input data was correctly formatted and it was compatible with the V2 model's requirement. This step included configuring the tokenizer to add necessary end of sequence and beginning of sequence tokens, which aligns with the model's architecture, and it also effectively manages the sequences during the training. So we also pre-process the dataset to fit the model's input requirements, which mainly focused on truncation and alignment of dialogue length, which is essential for maintaining consistency and quality in training. In the next slide, we're going to discuss about the training arguments and hyperparameters that were used. We set the batch size to 1 per device to manage memory constraint, which ensures effective learning. And then we've set the learning rate to be 2 times e to the power minus 4, which is optimized for gradual convergence without overshooting the data set subtle nuances. And next, we used gradient accumulation to effectively increase the batch size, which enhances the training stability. After preparing for training, we began the actual training process, which is central to our project. So the training of a model was meticulously planned and executed. We set a batch size of 1, and then after that, the training cycle details include we set a maximum of 200 steps, which balances the need for sufficient training against the constraints of computational resources. Then we set to evaluate the model performance for every 25 steps, which provides regular feedback of the training progress and model accuracy. And we also generated logs for every 25 steps to monitor the training process, and data is saved in logs for detailed performance analysis. So we also did model saving and checkpointing. So the model checkpoints at every 25 steps to ensure that the training progress is preserved and can be resumed for analyzed at any point. And the model data is stored in model underscore output, which is like organized to facilitate easy access and management. So next we go to evaluation and testing. So post training, our model underwent a rigorous evaluation phase using rogue metrics and quantitatively assessed its summarization capabilities. We particularly focused on the so basically rogue is like recall oriented understudy for gisting evaluation, which quantitatively assesses the quality and there are several rogue metrics, so which is rogue 1, 2, rogue L, and rogue L sum. So here, rogue 1 measures the overlap of unigrams between generated and reference summaries. Rogue 2 focuses on bigrams to evaluate the co-occurrence of two consecutive words. And the next one considers the longest common sequence of words, assessing sentence level structure and fluency. So rogue LSUM measures the longest common subsequence, crucial for assessing the coherence and sequence of ideas in the summary. After that, we performed zero-shot testing to evaluate how well the model can generate summaries for unseen dialogues, showcasing the generalization capabilities. And we use the dialogue sum test set, ensuring the model is evaluated on data and data that it has not been previously trained on, which provided an unbiased assessment of its performance. So next, coming to the results were highly encouraging. The model demonstrated significant improvements in all rogue metrics, with notable enhancements in coherence and detail, as evidenced by the rogue 1 to L sum scores here. Coming to rogue 1, it improved by 1.92%, showing better capture of key concepts. And rogue 2, it increased by 32.16%, reflecting improved phrasing and detail recognition. And rogue L rose by 4.39%, indicating enhancements in sentence structure and fluency. And rogue L sum rose by 15.37%, indicating enhancements in the summarization of longer text segments. So to conclude, let's summarize our project and its broader impacts. So the initial goal of this project was to enhance the Phi2 model summarization abilities using the QLoRA method, focusing on efficiency and performance. So the method that we used was to implement QLoRA to fine-tune the model on dialogue sum dataset, with an emphasis on reducing computational demands and memory usage. So the performance and enhancement that the project provided was an improvement in all the rogue metrics, with significant gains in rogue 1, 2, and rogue L sum scores. So our project also achieved reduction in computational and memory requirements, making the model more suitable for deployment in resource-constrained environments. Now, the key insights of this project include, it showed the effectiveness of QLoRA, which proved to be an effective tool for fine-tuning, offering a balance between maintaining high-quality outputs and managing resource efficiency. And it also showcased the importance of fine-tuning, and why fine-tuning of LLMs is important to tailor them to specific tasks and domains, enhancing their applicability and performance. So now we're going to show the Python notebook of our project. So this is how we initially installed all the libraries. And then at the end, this is how we loaded the data set and from Hugging Face. And let's go to the end of the notebook where we showcase the results. Yeah. So these are the results that we got. We can see that we've printed the absolute percentage improvement of PEF model over original model, where the rogue scores, the percentage improvement of each of the rogue scores. Like for rogue 1 it's 1.92, for 2 it is 32.16, and for rogue L it is 4.39, and for L sum it is 15.37. Thank you for your attention.